Yeah.
This is the later part.
Okay, good. Okay, thank you. Thank you for the introduction, and I'm very happy to be here today. I better be careful with that water. And I got that in case I get hungry. Just a second here. This is a picture of the prairie forest border. Actually, it's a picture of the triple ecotone, where the evergreen forests from the Arctic come south to meet the broadleaf forests from the Atlantic to meet the prairie from the Rockies, and they all meet in this place. Actually, it's a huge 100-square-mile area. And that's what the mixed prairie biofuel can look like in the fall, the grass, not the trees. Oh, by the way, I should say this, I followed the lead of one of my former graduate students, Richard Barnes, in the way I label the year, 02017. He said, always remember the human experience is just beginning. So one of these clickers worked. Oh, there we go. So mixed grass, mixed native plants of a region, which includes grasses, can grow on low fertility soil that's not good for farming. And then in the process of growing, they store carbon in the soil, at least if they're grown on non-fertile soil. And this buildup of carbon in the soil continues. We're not sure how long, but it looks like for the better part of a century or more. It hasn't been leveling off after 20 years of measuring it, still linearly increasing. If you want to see the details of this, you can look at a poster by Yi Yang on showing the graphs from this, and that'll be the first poster as you enter, I think, or else it's the last poster as you leave. Now, for comparison, burning 1 ton of fossil fuel like coal adds 3 tons of carbon dioxide to the atmosphere. But burning 1 ton of mixed prairie grass for biofuel from a diverse Midwest prairie, as a net effect, removes 1 ton of carbon from the atmosphere. And the reason that works is the carbon that's in the biofuel was pulled out in the spring, so it's not any net gain when you burn it, but there's carbon stored in the roots. And that amounts to 1 ton of carbon stored for every ton of biomass that you burn. And this becomes worldwide one of the Pacala-Sokola wedges, an additional wedge that they didn't have in their paper in 2004. And then if combined with carbon capture storage, I mean with deep earth storage, then this is one way of taking carbon out of the atmosphere during the 20th century. So I'll show you some carbon drivers that are increasing carbon in the air that make all this necessary. This is human carbon emissions and the blue is the empirical data, and the red is just an exponential curve I fit to it. Well, that exponential curve looks like it fits really well. So it looks like there is no hope here of doing something. But in fact, it's not good to fit exponential curves to increasing data because they often look like they fit well when they don't. And you really have to look at the doubling time. How is the doubling time changing? And so one way you can do that is not to plot the emissions versus time like I did, but instead plot the relative change in emissions as a function of emissions. This will show whether they're increasing or decreasing. And when you do that, that's what they look like. On the vertical axis is their relative change in emissions versus the total amount of emissions. And there seems to be a downward slope there in the recent years since 2 gigatons. And if you'd project that forward, that would say that we're at a leveling point at about 12 gigatons a year. Well, that was really a surprise to me when I drew this chart, that we could be leveling, even though that first chart looks hopeless. Now, whether we will or not, that's a question, but there's at least some hope there in that. Now, another one, the big driver of carbon, of course, is human populations. And so this also looks equally hopeless. That looks like an exponential curve going off to infinity. But when you do the very same thing to this, you'll see that something very big happened at that x in the mid-60s. It doesn't show on this curve at all. Can you see anything happening on that curve? But here's what happens when you put it in this other form of the relative population change as a function of the population. There's enormous demographic change in the 1960s. And there's no doubt that this happened, and I think everyone's recognized it now in demography. And it would put us, if we continue, heading toward 12 billion or 11 billion, which is what some people are estimating. It comes out of the simplest data analysis. But also one thing beyond this is that this is a graph made up by a colleague of mine, Evel Gorham, which shows the lifetime births per female as a function of the wealth of the country. And every country over 16,000 gross national income US dollars is below replacement. So populations in much of the world are actually declining. So both of these drivers then seem to be leveling off to give some hope that we might be able to get these things under control with some other help. So now I want to talk about the power of plants to help accomplish that. So let's see, I have 20 minutes, and I had a sheet that told me where I was supposed to be at each stage. I think I got rid of that. Or is this it? Oh, is this all being taped? I shouldn't be ad-libbing these comments like that, should I? So, yeah, okay, so the power of plants. The events relevant to this whole topic began at this lake thousands of years ago. Did anyone recognize that lake? Frozen over? This is Lake Vostok in Antarctica. And the lake there, in Minnesota lakes where I'm from, the lake on a cold winter will get ice 3.5 feet thick on it. This ice is 2.5 miles thick. And so as you drill down through that 2.5 miles, you go back hundreds of thousands of years to ice that was formed a long time ago. And in that ice is bubbles and dust. And you can then see what carbon dioxide was in the past. And that results in this well-known Pettit diagram. And so carbon dioxide in the air always seems to have been associated with temperature of the Earth. So there's, for 100,000 years, a slow decline in carbon dioxide, then for 10,000 years or more, a rapid increase during the global warming phase, then a decline. And in the last years, you can see the red, that's what we've done. So there's been about a 50, plus or minus 50 parts per million is the natural oscillation of the Earth between ice age and not. And we were at the end of that era at about 1776 or so. I picked that number just to be easy to remember. And then by the bicentennial, we had added 50 parts per million, and by now today, we've added another 50 parts per million. In fact, now, this year, it's gone up above the 400. So one thing that did is if we were about to drop into an ice age, as that curve maybe looked like, we stopped that. So I guess that's a good thing. But maybe we've gone too far. And so I'll just take this part and we'll spread that out. See, that's the most recent part there. I'll spread that out wide. And so if you took your portable carbon dioxide detector and waved it around each week like this in the summer, you would find this rapid, let me expand this just a little bit more. Starting in May, you'd see a very rapid drop in carbon dioxide. And then that would continue through the fall when the plants leaves. So what that is of course, as you know, I think, the leaves come out and they absorb carbon dioxide and they start producing wood and roots and they start losing carbon into the soil. And so that rapid downstroke, but there's always decomposition going on so that when that stops, then the decomposition is all you see and that goes up. So this amount of absorption actually is prodigious. It just looks like an up and down, but when I measured it, what you do is fit a regression line and ask, if the plants could somehow continue working for around the year, not have winter come, how long would it take for them to remove all the carbon from the air? That's simply doing a regression line and projecting to the axis. Is it 1,000 years? Is it 100 years? Turns out it's 19 years. 20 years approximately to take all the carbon out of the air. Now, we don't want all the carbon out of the air. That would be a global ice age. You want 1/4 of it out. All the plants of the world could remove the appropriate amount of carbon in 5 years. If you could capture it and not let it get back, of course, we can't do that. But if all of the plants of the world could do it in 5 years, then 1/20 of the plants of the world could do it in 100 years, and 1/20 of the plants, 5%. Well, in the United States, perhaps a few percent of the farmland is idle now anyway. So you could take some few percent of the land of the earth and use it for growing biofuel and capture the carbon and put it back into the earth. That would get rid of the carbon from the air in 1 century. And it would take a couple of centuries because there's other sources of carbon in the ocean than just the air. So that's sort of the idea. This really is just explaining in words what I just said. And so the general idea would be restore natural wildlife habitat on degraded farmland, especially abandoned farmland, and capture bioenergy as a byproduct of managing that restored natural habitat. By the way, when you have, at least in the upper Midwest, in this large area where you have prairie, it has to be managed somehow. One way to manage it with fire, by burning it in place. But another way to manage it is mow it, bale the stuff, and burn it as biomass. And I had an experiment that ran for 6 years on 1,000 acres to explore that and see what would happen to wildlife. And we found that it will actually help wildlife. In some cases, it won't hurt wildlife, typically. So mix the fossil fuels with this harvested biomass, and then capture a stream of carbon dioxide that's produced. Then sequester that carbon dioxide deep in the earth. So then optionally, when that carbon dioxide is deep in the earth, it changes its nature from being carbon dioxide gas. It becomes a supercritical state of matter, and it has essentially fluid as a gas, but with the heat absorption capacity of a liquid. So some people are saying, go ahead and take that energy back out and use it for a perpetual form of energy, renewable form of energy. So as I explained this to people, to different groups in Washington, oh, by the way, I should say, I hope in 50 years this all is thought to be silly. That someone says, oh, they were thinking you had to harvest 1/20 of the plants of the world to get carbon out of it. They didn't know about factor X. I hope that happens. But this is now, and so we have to think about what can we do now. When I explained this to various people a couple of years ago when this project was just getting started, I found in the Interior Department they loved this idea because this was new wildlife habitat. Instead of having abandoned farmlands, you'd have whatever the native plants of the region were. I talked to the people in the Senate Environment Committee, and some of them were pretty strong on burning coal. And this idea is useful to people who believe in burning coal because this is a way that you mix it with coal and it makes coal carbon neutral or carbon negative when combined with carbon capture storage. And then, of course, so one of the big security problems in the world is energy security, and so if every nation had something like this, it would help there too. So everyone in Washington seemed to like this when I talked to 3 different groups anyway. And then this is all part of the emerging topic of conscious management of the planetary ecosystem. So we used to be victims of the planetary ecosystem. Then we started becoming a global force and changing it without knowing what we were doing, not even knowing that we were much doing it. And now we're quite aware that we've made big effects on the planetary ecosystem. We've come to the point of thinking of consciously managing it. Now this is an enormous problem. Can we ever remotely understand the planetary ecosystem enough to manage it? This is one little piece of it, managing carbon in the air. So we know how to add carbon to the air. We're really good at that. How can you remove it from the air? You can remove it from the air with plants grown and then harvested, and so the root biomass builds up carbon from the air, and then if you sequester it, you can remove carbon from the air that way. So it's a feasible thing, and it's not like it's a small amount. It's enough that in 1 century we could fix all of this. So then, I could imagine this kind of a thing a century out or so, this kind of a thing statement, if we are able to remove carbon from the air as well as add it. I can imagine a statement that would say, the United Nations Climate Control Board, or whatever it would be called, has determined that we have lowered the temperature of the Earth 0.15 degrees too much, and so the participating power plants are hereby ordered to burn 40 gigatons of fuel and put it into the atmosphere. That's part of conscious management of planetary ecosystem. And that seems all pretty crazy. I'm going to close this off with a message from biogeochemist Evel Gorham, who I do still work with. He published his first scientific paper 70 years ago. And he was the guy who discovered nuclear fallout in the atmosphere, and he's the guy who discovered acid rain and worked on acid rain. Anyway, he jotted this little thing down when we were talking about conscious management of the planetary ecosystem. He jotted down this little statement on a paper, on a sheet of paper, which now we're using as the last paragraph in a paper we're publishing on ecology of the Anthropocene. So he said, it might seem unimaginable to that we can learn how to manage the entire planetary ecosystem, but we should remember that throughout our relatively short history, the unimaginable has repeatedly morphed into the commonplace. That's all I have.